that's an interesting little picture. Thank you, Jennifer Kearns-Lechner. And we liked it so much that I decided to take the next question from Jennifer Kearns-Lechner, who says, I think the first trip to another star system will wait until we have the technology to at least approach the speed of light. Generation ships are problematic in so many ways, and what's the point of that kind of commitment if humanity could develop warp drive before the ship arrives? What do you think? We have three kind of domains in that question. There's the much slower than light domain, which means that a ship traveling at the best speeds that we could put together today using chemical or nuclear rockets might take 100,000 years to get to the nearest star. 60,000, something like that. So the idea of a generation ship is you're traveling so slowly that the people live and die in the spaceship. It's basically a self-contained little world. And you have a generation that launches from Earth, and they wave goodbye, and they die, and their kids grow up and live on the ship, and they die and live and 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 die. And hundreds of generations later, you get to the destination, and that group of people on the ship get to colonize the planet. I don't see any way where that would work. I don't see any way where you could maintain the life support on something like that. The bigger you make something, the harder it is to move it. The thing about big bat problems that I think probably of all the things I like in that movie, is the idea that Earth is being invaded, being colonized, and the aliens send a mothership, and the mothership is the size of a softball. Because the less mass you have, the easier everything gets. So the generation ship is an interesting idea, but I don't really buy it. Suspended animation is the idea that you would basically have one crew at launch and the same crew at the destination, and you would basically find a way to suspend them, keep them alive at either zero metabolic rate or a very low one. And when I was writing Aurora, I did a year's worth of research on this subject. You often see suspended animation lost in space. You step into a tube and so on, and sometimes you see them kind of, in a little force field thing appears in movies that are more serious, like the Alien movie or Aliens. You see people lie down in beds and they kind of get pressure sealed, and you can tell it's cold in there, so we know that we're making them colder, which is in fact a good way to keep your metabolic rate down. And it looks like this new movie, which is coming out, Interstellar, looks like they're taking that kind of thing even better. They're submerging them in liquid, which is a better way to support your body weight, and and all kinds of other interesting things. But suspended animation, at least in the way we understand that term, is just magical. It just doesn't really exist yet. Having done some research on this, I can tell you what does exist. The lower you get the body temperature, the more the heart rate and the oxygen, the respiration rate both go down. And the metabolic rate slows down, but it doesn't stop. I mean, you might go down to 6 heartbeats a minute, down from 60, 40, 50, 60 at rest if you're very calm, 80, 90, 100 if you're a little more excited, and 120 if you're really thrilled. So you can slow it down. But one thing that I did find that is interesting is that if you expose mammals, I want to say it's sulfur dioxide. I had the research. I'm pretty sure it's sulfur dioxide. Rotten egg smell, I think, that gas. If you expose them to a small percentage of it, 16% or something like that, breathing sulfur dioxide actually does dramatically slow their metabolism down. And if you combine that with low temperatures, then you can get to a point where people are out for relatively, they're down. And so when we're talking about a mission to Jupiter, what I basically was doing, I had them set up so that they were doing all three. The best way to get I'm talking about current technology now. The best way to get people unconscious and keep them unconscious is to put them in a medically induced coma. We do this all the time when you have burn victims, people who are in enormous amount of pain and had skin grafts, and they basically just have to lie still and heal for 6 weeks. They just put them in a coma, a medically induced coma. They keep them on sedation. Same kind of anesthesia that you would use for surgery is a slightly lower level. And so in Aurora, having given this very serious thought, I had a mission that was about a year. It was about 11, 12 months out and about 13, 14 months back. And the main reason I wanted those people unconscious was because did all of Aurora as if I was going, as if this was a practical problem I had to solve. So you do save on the foodstuffs and the supplies, and you save on oxygen, although if you've got a reactor, you probably make your own oxygen. So you save on consumables, rather. And there's some other advantages to have people unconscious. If you put them unconscious, you can keep them in a little crypt, basically. And rather than having to shield the entire ship, if most of the crew is spending most of their time unconscious in a bed, basically, you can just shield the bed. So that helps a bit with the radiation shielding. The more shielding you put on a ship, the heavier the ship gets. The more heavier the ship gets, the more fuel you have to carry to get the same delta V. The more fuel you have to carry, the more fuel you have to carry to advance and accelerate the fuel, and then you have to carry more fuel to slow the fuel down, and then so on and so on and so on. So what I did in Aurora was I did all three. I had a doctor, the guy who's in charge of the hibernation of the crew, is in fact a medical anesthesiologist. He's an anesthesiologist, and he is a guy who spends his medical career keeping people in a state of sedation. So what they did was this guy in his lab, this doctor, fictional doctor, in his lab was experimenting with dogs and hamsters, and he had a hamster that lived, for like 7 years, and so what he does is he basically gives him a shot, like you'd get if you're about to go into surgery. He hooks up a little catheter into the wrist, and he says, "I'm going to give you some lovely drugs now." And the room starts to spin, count backwards from 100, 99, 98, boom, they're out. Once they're unconscious, he adjusts the oxygen and sulfur dioxide rate, puts a little sulfur dioxide in there that absolutely starts to slow the metabolism down. And then he basically takes their temperature down to about 60 degrees, their core temperature down to about 60 degrees. And then your heartbeat goes down to 3 beats per minute. Respiration goes down to about 1 or 2 breaths per minute. And you can keep people down for a long time that way. The problem is you feed them through a tube, and you have to worry about getting the waste out. See, this is the thing that I try to do with Aurora's so-called suspended animation. I wanted to make it messy, because it is messy. It's extremely messy. You have to feed people through a tube. You keep a tube in somebody's mouth or in their throat long enough, that's horrible. Bed sores are an issue. I had these beds actually rotating because the ship has centrifugal gravity for the people that are awake. So you got that thing, and you don't want them in weightlessness anyway because their bones start to atrophy. So it actually rotates them like a rotisserie so that they're not constantly on the same side. You develop bed sores that way. You got to feed them that way. You got to keep them hydrated. You got to keep the drugs going into them. You got to keep the sulfur dioxide going into them. You got to keep the temperature down. Got to do all these things. Got to be monitored. And so I basically figured that on a mission of 2.5 years, that what they would probably do is they might do 4 to 6 down and 2 up. That was the way I looked at it. You have a crew of 7 on that show, and what the basic premise was once they got past lunar orbit and they were in cruise mode, at any given time, they would put 3 or 4 of those people down and leave 2 or 3 up. Doctor was always awake. He was kind of a loon. He was the kind of guy who liked to study Chinese, and he perfectly happy to be in solitary confinement for the rest of his life because he's just a complete intellectual. And I was actually thinking of getting Dwight Schultz to play that kind of a weird sort of mad scientist kind of thing. But basically what happens is you would, one of the things that you show them doing is before they go in and one by one start going down for the first time into this hibernation state, they give them the diaper, and there's various tubes that have to be attached, and so that's not pretty. They have to have tubes down their throat. That's not pretty. So when you see them there, they're not lying there like Ripley in their little cloth underwear, calmly sleeping. The thing they got tubes taped to their mouth. They look like people that are in the intensive care unit. They got tubes taped to their mouth. They got tubes going in their arms. They got tubes coming out of them in various places, and it's uncomfortable. And when they wake up. When they finally wake them up, they're incapacitated for a day or 2. The first 6 hours, they're utterly lost. I've had general anesthesia probably twice, and because I'm always curious in the procedures and how they work and stuff. So the one thing I remember both times about being under general anesthesia was asking the doctor, "Is everything okay? Did it turn out okay?" And having them say both times something to the effect of, "For the 8th time now, Bill, yes, everything came out just great." So, your memory's shot, you're physically ill and weak for a day or two. You're probably throwing up. It's ugly. It's a messy, ugly, gross thing to do. But it's cool and it's believable. And I think that's really the answer. So that'll get you, let's say you could put people out for 6 weeks, 8 weeks, 10 weeks, a couple months. If you keep them out much longer than that, you run into the problems that you have with people who are in medical comas for months and months and months and months. Body starts to atrophy, bed sores, problems, everything just goes south on you pretty quick. So I figured 6 weeks down, 2 weeks up, 6 weeks down, 2 weeks up. Get them back up, get them into shape, get them on the treadmill, get them on an exercise bike, work them out, get them back to normal, then plunk them down again. That kind of thing, or some variation on that thing, would probably get you through the solar system. You'd probably be able to get most of the solar system. Vipercheck wants to know which version of Dwight Schultz, Lieutenant Barclay, the only coward in Starfleet, or Howling Mad Murdoch. It won't be either of those, but it'll be more like Barclay than Murdoch. He's the perfect guy for this. He's the perfect guy. He's alone on the ship for most. A lot of times he's the only guy awake. On the way back, he is the only guy awake because the ship's all torn up and we've lost some people, and he wanders around naked. Because why wear clothes? That kind of thing. Anyway. That kind of thing could probably get you through the solar system. And as technology advances, we might find what it is about sulfur dioxide that's doing it. I think a very promising way to look at suspended animation is through genetic modification. Bears hibernate, and some other animals do too. And they go into an actual genuine hibernation, and needless to say, there's no one pumping drugs into bears or chemicals or any of that stuff. The bears have a genetic component that activates when certain temperature and lighting conditions and all that other stuff happens. And they go into a deep and effective sleep. And the great thing about what we're learning about genetics is that so much of this stuff is interchangeable. If you have a gene that turns on spots on a frog, for example, and you transplant that gene onto fruit flies, then they start developing spots on their wings. And that kind of thing really is remarkable. So I think if you started getting into this seriously, like you had an actual space program and an actual series of places to go, you'd start getting into the genetic thing, and then you could probably find a way to have your body turn itself damn near off. Coupled with the technological boost, you could get people in much better shape there, I think. This business about stasis fields and stuff, I just had a rule for Aurora, and that's no magic. No matter how much I wanted something, I couldn't, if it wasn't feasible engineering-wise, then it wasn't going in there. So that's it for the hibernation thing. So generation ship, I think, is out of the question. The question is faster than light or relatively high sublight. A generation ship, by definition, is a sublight ship, but it's not even close to speed of light. If it's taking centuries, even forget 10,000 years or 100,000 years. If it's taking more than 100 years to get someplace, it's a generation ship. You're moving pretty slow. So let's deal with the faster than light thing, and we'll save the good stuff for last. Up until a couple of years ago, the first half of my life, I was utterly convinced that warp drive was just a matter of time. Faster than light travel, I thought there were lots of different ways to do it. One of the things I thought of as a kid, now I don't know if this is unique, it's unique to me, I hadn't read it anywhere, but I thought, if space-time is actually one thing, if space-time is a single thing rather than space and time, and space-time is a single thing, time is moving through the fourth dimension, I had a thought that was kind of interesting, and that thought was if you could drop yourself out of time, it didn't matter how fast you were going. You could throw a baseball to Alpha Centauri. If that baseball was not moving through time, then it didn't matter. You literally just stop the time on the vehicle and turn it on again when you get there. That's different than relativistic time dilation. I'll get to that in a minute. But anyway, but then for the last 15, 20 years, I thought it was absolutely impossible, because I'm almost sure it is absolutely impossible. I have to be careful about wishful thinking, Of all the things that science fiction writers and readers and techies and space kids and all, of everything we want, the thing we want most is faster than light travel. And because we want it so bad, it makes us prone to believe it's going to happen. Up until very recently, it seemed to me that whatever experimental shreds of evidence there might have been for being able to travel faster than light through a wormhole, let's say, you find out that in order to open the wormhole, you have to have more energy than 10,000 solar systems create, and the wormhole is a couple of molecules wide, and there's no way to aim it or steer it. And frankly, it just started to feel like, yes, theoretically, I suppose this might be possible, but that doesn't mean it's possible or doable. And I still think that's the case if I had to bet. If I had to bet, I'd say that faster than light travel is technologically impossible. Although, as we'll find out a little later on in the show, maybe not. So I think faster than light travel, at least for the foreseeable future, and when I say the foreseeable future, I mean the foreseeable future. We're looking at energies unimaginable, really. I say it doesn't exist, and I don't think it's going to exist. Which leaves us in the world of sublight travel at relatively decent speeds, which is attainable. As many of you know, Einstein's theory of relativity predicts many things. And these have been proven experimentally. It's not up for discussion. It's not like global warming where there's a computer model that says that this might happen. We've put extremely accurate clocks in airplanes, and we put a couple of extremely accurate clocks in orbit, and they do, in fact, slow down. And time slows down for you when you're on an airliner, slows down for you a little bit more if you're in orbit. And your time slows down for you a little tiny bit if you're traveling on the 405 freeway at 20 miles an hour. But obviously, these are utterly insignificant. A second, if you're traveling in orbit around the Earth, somebody probably knows the exact answer. But if you're moving at orbital speeds, the time dilation is so slow that you might pick up a second every 100,000 years, something like that, right? So the problem with the time dilation, which is good, if you start going faster and faster and faster, time slows down for the crew. That's good. That's great. If you traveled at 99% of the speed of light, time on board the ship would really crawl, and you'd turn on your speed, your sublight speed drive, and get up to high relativistic speeds, and next thing you know, you're there because the time is slowed down for you. That's awesome. That's great. The problem with that is that the time slowing down, the time dilation, is more or less linear with the increase of the mass of the ship. So as you go faster and faster and faster, your ship gets more massive. And it does three things. Time slows down, the ship gets heavier, more massive, and it compresses along the vertical axis as it gets shorter in the direction in which it's headed. None of this is perceptible to the people on the ship, obviously. That's why it's called relativity. But the problem with that is that as you get faster and faster and faster, your ship is essentially heavier. I'm going to say more massive, but for the sake of the argument, I'm going to say heavier. It's a little easier term to understand. More massive is the correct term because weight is only mass in a gravity field. But the ship gets heavier. And the problem with that is that it takes a certain amount of push to move a 10-ton ship. And if you have to move a 1,000-ton ship, you need a lot bigger push. And if you have to move a 100,000-ton ship, you have to have a much bigger push than that. And if you have to move a 1,000,000-ton ship, that's an even bigger push. And that ship is getting heavier and heavier and heavier, more and more massive, as you get faster and faster and faster. So what I deduce from this is that even if you could get there in terms of the propulsion, you're not going to get time dilation effects of any magnitude, because once you start getting time dilation effects, you start getting mass increase effects, and mass increase is the end of the world as far as propulsion is concerned. Now, I am assuming that this is all reaction-based rocket-type propulsion systems. We'll get into those in a minute. There might be reactionless drives that invalidate all of this. If that happens, they probably require more energy than we could produce. But let's say that, look, there's always something that could happen that we don't know about. I'm just talking about what we know about today. A reactionless drive, something that just moves from here to there for warp reasons or whatever, is a game changer, and we can't speculate on that. So that does leave us with one option, and I think this option is actually a viable option. I think if we're talking about interstellar travel, I think the most likely way for it to happen, if it ever does happen, is to develop some of the technologies that we have on the board today. And if you were to use everything right, you probably could get a ship up to 20 or 30% of the speed of light and slow it down again at the other end, 30 or 40%. Let's say 50%, because 50% is a nice number. At 50% of the speed of light, you don't have any noticeable time dilation effects. They're exponential, so is the mass gain and foreshortening and everything. At 50% of the speed of light, if you could get immediately to 50% of the speed of light, you would be in Alpha Centauri in 9 years. Given some of these, look, people could live for 9 years. People have done 9 years in prison. So even without putting the crew under hibernation, your suspended animation, whatever you want to call it, you could probably get a crew there. So I think it's actually feasible. So let's say 50%. That's a tremendously difficult thing to do. To give you an idea of how tough it is to get up to 50% of the speed of light, my understanding is, there are people out this smarter than I am, but in order to get to the speed of light, if you didn't have this mass increase effect, if the speed of light was just a linear thing that you got to, you'd have to accelerate at 1g, which is a rocket that's pushing down, accelerating fast enough to give you 1g worth of weight on the floor. You'd have to accelerate at 1g for a year. A long burn today is measured in minutes. A long burn is measured in minutes. We're talking about a year. What is that? I'll tell you in a second here. So if we were if we had a rocket engine that was powerful enough to produce 1g of thrust and you wanted to get to 50% of the speed of light, it's like people used to know how to do math. So you need it for 6 months. So 60 seconds times 60 equals 3,600 minutes. That's in an hour. I'm sorry. Yes. Times 24 hours times 180 days. That's a burn of 15,552,000 seconds. 15 million seconds of burn, as opposed to, some of these burns, most of these burns are 30 seconds, 60 seconds, 2-3 minutes, that kind of thing. That's a lot of impulse. It's a lot of delta V. But it's theoretically possible. And obviously, the slower you go, the longer it takes, but it's theoretically possible. So to answer your question in a very long, roundabout way, Jennifer, I think it is possible to get to other solar systems. I think it's possible to get to other solar systems by achieving the most efficient drive you can, staying close, using everything you can to keep the fuel weight off of the ship. That might mean beamed power to get you started. That might mean things like, gravity assist, catapults, strap-on boosters that fall off, whatever it takes, just get you going. And then just carry enough fuel to slow you down. Ideally, you could slow down in a planet's atmosphere. There's any number of ways you could slow down. Just take the least fuel with you. So I think it's doable. But it would be doable using extremely efficient engines, some form of suspended animation, although I don't really much like that term anymore. And then patience. One final thing about space travel at interstellar travel. Clarke, as typical, Arthur C. Clarke dealt with this issue. When you're moving at those kind of speeds, 10% of the speed of light, 20%, 30% of the speed of light, 50% of the speed of light, when you're looking at those kind of speeds, if you hit a particle of dust, the kind of dust mote you see floating in the room, that'll probably take out your ship. It is the kinetic energy of your vessel is so high, and there's so much energy on it, that if you hit anything, you're going to have a serious problem. And when I think something like a P or a BB is the end of it, it's the end of the ship. Ship's vaporized. So what do you do about this? It's true that there's very little space, there's very little junk in interstellar space, very little dust, very little, virtually no rocks. This whole business about meteors is all nonsense. But you have to face it. If you hit a particle of dust on the way, everybody dies. Clarke solved this problem in a pretty interesting way. He had a vehicle on one of his things, I forget which one it was, that had a giant ice, like frozen seawater, on the front of the ship, which was heavy and you had to move it. But it was basically, I don't know, scores of feet thick or something. This is a giant block of ice up front, and this thing took the impacts of small grains of sand or dust motes or whatever. You hit anything bigger than that, you're done. But there's not many of those things out there. Anyway, it's something that not many people talk about. Obviously, on things like Star Trek, on the Enterprise, you've got deflector shields and screens that are blowing all this stuff out of the way. But that raises the question of how do you project a force field faster than light? And you start getting into things like space warps, and we'll talk about that a little bit at the end. Although this one's already an hour and 8 minutes. We're 2 questions in, so that's okay. It's fun. So let's get back to the solar system, because the solar system at least is something you can speculate on. By the way, this will curl your hair. If we were to say that interstellar travel is 100 years from now, let's say we can do it in 100 years. Movies are about 100 years old. If you look back to one of the first movies ever made, it's what was his name? I want to say it's Lumiere, but I don't know if that's right. Back in the very late 1800s, I want to say 1896, 97, there was a movie made called Journey to the Moon, or From the Earth to the Moon. It's a Jules Verne thing, in black and white, done with cardboard props. That movie that Scorsese made was based on that guy, Hugo. Anyway, my point is this. If you look at those guys getting in that artillery shell and then wandering around on the moon, that was 100 years ago. If you look at some of the corny stuff from the 1950s, cut the rockets, rocket 2, and you've got these oscilloscopes and they're using like mechanical relays and levers and all that other stuff. That was only 40, 50, 60 years ago. What I'm trying to say is the actual vehicle, the actual technology will probably look as different as stuff 50, 60 years in the past does. If you look at these guys like the Flash Gordon serials and how awful that stuff looked and how silly and absurd it was, and how silly and absurd some of this 50s spaceships were, our best guess is probably going to look that silly or absurd 100 years from now. It's kind of shocking, really. Although, with that said, 2001: A Space Odyssey holds up so well. Anyway, here we go.